We'll look at example 3 on page 711. And it says an object travels at a steady rate along a straight path from point -5,3 to point 3, -1. Now, what it's saying is if we were to start at the point -5,3 to 3, 1, 3, -1, this object is traveling from this place to this place. And as it travels, it's traveling through a vertical component and a horizontal component. So what we're trying to do is we're going to try to put the two things together. On the x-axis, it's actually traveling from this point, because that's even on the x-axis with our starting point, and it's traveling to here. So it's traveling from here to here in its horizontal component, so along the x-axis. It's traveling from 3, which is here, to -1 on the y-axis. So if we can look at it this way. So we have these two components that we're looking at. And this will make actually even more sense when we get into vectors, because vectors have a horizontal and a vertical component to them. So when you move, you're actually moving along your vertical and your horizontal component. So what you're actually trying to do is you're trying to figure out where this object is along that path after a certain amount of time. So you have a place that it starts, which is here at the point -5,3, a place that it ends, and the example says that it takes 4 seconds for it to go from its beginning point to its ending point. So what you're trying to do is you're trying to figure out where it is at 0 seconds and 1 second and 2 seconds and 3 seconds and 4 seconds, so that it starts at 0 seconds and it ends up here at the end of that time period. And you're trying to figure out where is it along that path during those various time frames. So what you have to do is you have to think of each component in terms of time. So the horizontal component, which is the one going across the x-axis, and the vertical component, which is the one going across the y-axis, they each have an equation. So if you think about what's happening, this one is changing from the number -5 to 3. And if you think about distance and time in relation to a linear equation, the rate that it travels would be its slope. So you have rise over run. So in this case, this is changing by 8 meters because it's going from -5 to 3. So if you just take the difference there, you've got 8 meters. And that's over the course of 4 seconds. So that would be 2 meters per second. So every second that it travels, your x value is changing by 2 meters for every second that it travels. And remember that the b value is what we call the y-intercept. So if you're looking at this equation at -5 and the 0.3, and we're trying to just look for the intercepts that we're looking at, and we were just looking at just the x-axis, we would actually be just looking at the x-intercept. So we would be saying, okay, where is this on the x-axis? Where does it start? Where does it end? And we would have an equation that was 2 meters per second, and it starts on the 5. And what we could do is just for that one component on the x-axis, we could say, well, if we were just traveling from this place to this place and it took us 8 seconds to get there, we would be traveling 2 meters per second. And so that's what this equation represents. And you can do that for any equation that's linear like that. So we can do that again for the y value. If we're going on the y-axis, we are starting at, let's see, we start at 3 and we go to -1. So if you go from 3 to -1, you're going down 4 meters. So you're going a -4 because you're going from here to here. And that's a distance of 4 meters down. So we would always use a negative to represent down. It's just direction. So if we're going down 4 meters, and it's taking me 4 seconds to do that, that would be a time of -1 meters per second. So we would do the same thing we did up here, and we would say that's a negative t because that's -1. So -1, and we started, remember where we started here, we do use our starting point. So we started on the y-axis on 3, so we would say +3. So that would be our equation for just the y component. It's our starting point, which is here on the y-axis, and our rate that we're going. So that's the two components that you have when you're doing that. Now, we're trying to build and we're trying to figure out where this object is after each time frame that we have. So let's put this on another slide. So we have x of t equals our 2t minus 5. And we have y of t equals -t plus 3. So what we would need to do is build a chart to figure out the position. And we would say, okay, after 1 second what happens, and 2, and 3, and 4. Because everything ends in 4 seconds in this particular problem. So we have one equation here, and one equation here in terms of time. And we just need to simply fill in those values. If t is 0, we would say 2 times 0 minus 5, and we would get -5. If t is 1, we would say 2 times 1 is 2, minus 5 is -3. And we could go on and substitute those numbers in there. So you can pause the video if you need to, make sure you understand the math. We could do the same thing for y. If we put 0 in for t, -0 plus 3 is 3. If I put 1 in there, -1 plus 3 is 2. And so forth. I could keep doing that. So again, pause the video, make sure you understand the math. So what we have when we do this is we have ordered pairs that represent the position of my object. So I'm saying at 0 seconds, I'm at the point -5, 3. And we knew that because that's how it started. It started at the point -5, 3. And look what happens at the end of 4 seconds. In this particular problem, it ends at 3, -1, which is what the problem said. These are the places that they are in between. So at 1 second, it's at the point -3, 2. At 2 seconds, it's at the point -1, 1. At 3 seconds, it's at the point 1, 0. And let's see, let's put that on another slide so you can see it. So if I were to graph that, if I were to graph my first one at the point -5 and 3. Remember, that was my starting point. So that was at 0 seconds. At 1 second, it's at the point -3, 2. At 2 seconds, it's at the point -1, 1. At 3 seconds, it's at the point 1, 0. And at 4 seconds, it's at our stopping point of 3, -1. And I can connect these, and I can say, and that's not a very good line, but I can say that I'm going in that specific direction. I'm going down. And remember, this is what our graphs look like when we're doing parametric equations. We have the direction also graphed with it. So this is what the two components together look like. And if you were to graph them separately, what you're doing, if you'll look on page 711, you'll see figure A is the graph of the first equation, the 2t minus 5, where it starts at -5 and has a slope of 2. Figure B is the graph of -t plus 3, and figure C is where we've put those two together. And this is what's going to happen when we do vector addition later on.